The next and last thing on this piece is, as we were going through that assignment, that 4.1 thing, we were talking about energy level transitions, electrons moving from one energy level to another. For some reason or other, I seem to remember introducing exothermic and endothermic yesterday. Did we discuss that? Okay, so as an electron moves from one energy level to another, oh, I know, I did a really good job in my other period. And I think I did this and said, okay, we all concluded this was hydrogen. One proton, one electron, da-da-da-da. And if energy is added in an endothermic sense, meaning that's going to be a positive energy, okay, we can get, if we have enough energy, we can bump it up to another energy level. If we add a little bit more energy, we can get it up to another energy level. Anybody notice what I did there? Why did I use different colors? Not Christmas. Good try. What's that? Different amounts of energy. So to go from here to here really requires only a little bit of energy, whereas to go from here to here requires more energy. Okay? And red and green on the electromagnetic spectrum, which one's lower energy? Red. We already discussed that, right? Okay. Let me see. Oh, and then the last thing I wanted to do, you saw that word photon, I believe, is in one of the answers. Yeah. Okay. And we had talked, you may have read in there, did you read anything about energy as being quantized? No. Did that word come up?
I got confused by that.
Was the word quantum in there somewhere? Yeah. Okay. Does anyone know what that means? And it's okay if you don't. It kind of is. Okay, so for energy to be, to describe energy as being quantized, it's not a continuous, and I've got a couple of different analogies. Your book used one analogy. I'm going to use a slightly different one, but works the same way. A slightly different analogy. Instead of energy being a continuous, like an infinite amount of energy gaps, energy is quantized, meaning that it can only have specific values. Here's a good analogy, in my opinion. So, you know where guidance is? The guidance office. Okay, that hallway. Well, as you know, the hallway is at two different levels, right? You guys have two different choices on how to go down that hallway. You can either go up the steps, or you can go up that ramp. Would you guys agree? Okay. So, the steps represent energy as being quantized. They come in little packets called photons, okay? But you can only have discrete little packets. It's not a continuous thing. So, just for fun, I'm playing with the numbers here. Flat out playing with the numbers. I'm just making things up. Let's imagine that each step represents 10 joules of energy. I'm making these numbers up. You guys get that? Mm-hmm. Okay. So as I'm going to go, I decide I'm going to go up the steps, and as I get up to that first step, I'm only going to put 8 joules of energy into my step. What's going to happen? I'm going to fall down. I'm going to trip. I've seen this happen. Some of you have probably seen this happen. That happened to you. Happened to Kirsten. Okay, but anyway, are you going to make it up to that first step? No, and if you continue, your momentum might actually cause you to fall over, okay? All right, so you don't make it because you didn't have enough energy. What if you put 12 joules of energy into that step? Where are you going to end up? On the first step, because there's nothing between 10 and 20. So I have to have enough energy to get to that point, but in order to go to the next step, I have to have 2 units of that. Does that make any sense? So that's why they say energy is quantized. It comes in little packets. Each packet is worth a certain amount of energy. Whereas if you go up the ramp, you would have an infinite amount of energy possibilities there, right? That is not how energy is organized. Now, we never know this because the energy little packets are really so small and there's so many of them that it looks like it's kind of continuous to us. It seems like it's continuous. But electromagnetic, electromagnetic radiation is quantized in the sense that the energy packets are discrete quantities. So when we've been calculating some of these energies, that's the amount of energy for an electron at a particular position. This whole idea is what explains this whole energy level thing as we get through that for the rest of the week. All right. With that being said, there is a little equation that we can use. So let's go back to this. To get the electron to move to higher energy levels or further from the nucleus, we talked about the whole centripetal acceleration thing balanced with the electromagnetic. Okay. To get the electron to move to higher energy levels, energy has to be added, which is an endothermic process. We would give that whatever energy associated with that a positive value, whereas for the electron to jump back down to a lower energy level, that would be an exothermic process in which energy is released in the form of some sort of electromagnetic radiation, which we played a little bit with that yesterday. Okay, there is an equation that kind of relates that together. So just go ahead and throw that equation into your notes somewhere. So now we've got like what? 3 basic equations, and we can do all kinds of things from there. Abby, I was right. I can't believe. It's a discussion that Abby and I were. Actually, it was a one-sided discussion. Abby sat there and stared at me currently, just like she's doing now. Okay, so this is a constant. So notice delta. You guys all remember what delta means. Change in, actually, no, let's be more specific here. Final minus initial. You guys have to drill that into your brains, okay? It's always final minus initial. Okay? Anyway, this value right here is actually, it's a constant, and interestingly enough, it's derived from 3 other constants. 2 of them you know. Planck's constant and C, the speed of electromagnetic radiation in a vacuum. And then the third one is something called the Rydberg constant. Don't worry about it, because if you have 3 constants and you put them all together, you get another constant. Okay? But anyway, it's negative 2.178 times 10 to the negative 18 joules. Now, what does the rest of this stuff mean? Write the equation down as I have it. You already did that. Okay? But I'll tell you what this represents here in a second. It's actually not technically correct, but for our intents and purposes, for what we're doing with it, it is. Because what element is all of this information based on? What one type of atom? Hydrogen. Okay? Now, the 1, you don't have to write this down. You just tuck this in your little brain and save it for whenever you need it about 3 or 4 years from now when you're taking physical chemistry. Okay? It actually represents the letter Z. The letter Z represents the nuclear charge. Well, what's the nuclear charge of hydrogen? 1. So I just wrote it as 1. Okay? Yes, Peyton is here. You know what? It's kind of funny. I looked at her first and I said, no, it can't be her. Well, that's a long story. I really don't want to go into it right now. But she was tardy. Yep, but. All right. So anyway, yeah. So Z represents the atomic number or the nuclear charge, but for our intents and purposes, it's a 1 because we're only talking about hydrogen. So I just went ahead and threw the 1 in there. The N represents the energy levels that we're speaking of. Now, you guys already know, first energy level, second energy level, third energy level, so on and so forth. So, the 2 represents final, the 1 represents initial, and those values are squared. Everyone got it? So, just for fun, what I would like you to do, let's imagine an electron that has gone from the 4th energy level. Before we do that, if we go from the 1st energy level to the 3rd energy level, if an electron is moved from the 1st energy level to the 3rd energy level, okay, what is this value? What is going to be the sign within this value? Going from the 1st to the 3rd. I'll let you contemplate that for a moment. Do we have a sign? What's the sign going to be for this value? The value in here is going to be negative, right? And then we multiply by a value that's negative, therefore positive. Does that make sense?
Yeah.
Going from 1st to 3rd, energy would have to be added, right? On the other hand, if it went from the 2nd to the 1st, this value would be positive, multiplied by the negative would give us a negative, and energy would be released in an exothermic sense, right? Does that make sense? Okay, I just wanted to get it so you can kind of get a sense of which direction the electrons are moving based on that idea right there. Okay, well, with that being said, let's just change it up a little bit for my other group. Let's say we have an electron that went from n equals 3 to n equals 1. What type of electromagnetic radiation would that represent, or would be associated with that transition? Ready, set, go. Feel free to discuss amongst yourselves. You have all the information you need embedded within 1 to 2 pages of notes. Other than the fact that you're going to need your electromagnetic spectrum, it's in the books. That's why I said feel free to talk amongst yourselves. Section 4.1. I don't know pages. I know sections. The pages change depending on what book you're looking in, but the sections. get here today? You look a little stumped. Oh, well, then that too, huh? Sam's currently going. Hi. I'm sorry, what? How so? Come on, keep going, keep going. I know your question. What is, you have an answer, what is your answer? Joules, which is a unit of energy. Watch this, watch this. Where is energy represented on there? You just figured it out, didn't you? Yes. That's where I did my error. Remember I said you're probably going to need information from a couple of pages of notes. Very good, very good. I did too. At a minimum, how many steps need to be done in this question to answer this question? At a minimum, 2. Some of you might choose to go 3. All right, so here we go.
Wait.
I don't know. No idea what the answer is. I just throw out the questions. You guys come up with the answers. Is that what you guys came up with? To start? Right? I don't know what that value, does anybody have that value available? I don't know what that is. So 0.88, yeah, because 1/9 is 0.11, so 0.88, so what is it? Point what? Okay, so, and then we multiply that by the negative 2.178 times 10 to the negative 18th. I'll bet you're in calculus, aren't you?
I'm in pre-calculus. I'm a sophomore.
Okay, well, the reason I asked that is you gave me an answer in a fraction.
Oh. Well, fractions are cool.
Okay, but where I'm going with that is if I gave you all the, if this book gave all the accepted values in fractions, how would you guys like that? You know what I'm saying? So we have to have answers that actually have relevance to significant figures and such. But anyway, what do we get for the entire value for the energy? I'm sorry, what's that again? 1.936 times 10 to the negative 18th joules, which makes sense. This is about 9/10, and this is, yeah, it makes some sense, doesn't it? Okay, so anyway, does the negative sign make sense?
Yeah.
Because energy was released, right? Okay. At that point, we just take the absolute value because clearly you can't have a negative frequency or a negative wavelength, okay? But anyway, at some point in time, most of you chose to go that direction, I'm hoping, okay? And from there, we can solve for nu, right? Which is E over H. And it's just a matter of plugging and chugging. So we take that value and divide by 6.626 times 10 to the negative 34th joule seconds. We can check our units. Joules cancel. We're left with 1 over 1 second, which we know as hertz, which is a unit of frequency, right? Peyton, is that where you ended up going? That okay? After I asked you what does this mean, you said, oh, okay. And so now I don't know what that comes out to. Does anybody have the frequency there? 2.922 times 10 to the 15th hertz. Okay? It doesn't matter. No, it's not negative for the reasons that I said about 45 seconds ago. So all we have to do now is look at our handy-dandy little electromagnetic chart and see where that radiation may lie. I don't even know. So about 3. So what are you guys thinking? UV? Towards the beginning of it, right? Just outside of the
I just kind of
visible?
wrote. Yeah, just I wrote ultraviolet.
Okay. Well, there we go. Not too difficult, is it? It's just the numbers are a little bit different than what you're used to. Other than that, it really is. Okay.